let's just keep going with internal loads. So back to internal loads in beams. And the example that we did was you have a beam with a pin joint here. This way, there's a roller at the midpoint. This distance is 0.5 meters. This has been acting all funny recently. Okay, 0.5 meters, and then this other half is 0.5 meters. And there's a 1,000 Newton load of downward force here. And then there's an external torque of 500 Newton meters here. And last time what we did was we calculated the internal loads at that blue line. So last time we calculated the internal loads at this location. Using a coordinate system sign convention. And what I mean by that is that whenever we calculated those internal loads, we thought about the point of contact as a fixed joint, and the fixed joint we represented as providing an X component of force, a Y component of force, a Z component of couple, and a X component of couple, okay, in this coordinate system. So we're using this coordinate system. And we were able to do it. Does anyone remember what the problem is with that? With using that sign convention? So the problem with using a coordinate system sign convention is if we happen to isolate the other half of the beam to calculate those internal loads, so if we isolated the other side of the desired location, all the internal loads would be opposite signs. So the calculated internal loads would switch signs. And what we want is a single set of internal loads that we can, no matter how we calculate it, we're just going to say at this location, the internal loads are this. So we're going to come up with this new sign convention that doesn't just depend on the coordinate system, that we can use from either side, and it's going to give us the same answers. Okay. So the next two steps are these. First, we're going to introduce a new sign convention. that doesn't have, so without that Newton's third law problem, the thing above, the reason that you switch the signs if you switch which side you're isolating. And that's going to look like this. So when you think about isolating a point on the beam, you can think about it as being an infinitesimal sliver. Okay, that is a finite sliver, but imagine it being infinitesimally thin. Then a positive value of what we were just calling the x component of the force before. On this side would be this way, and this side would be this way, and we'll just call that capital T for tension. Okay. So now if we isolated the beam the way, if we isolate the beam the way we did before, this half, then a positive value of T is that way. If we went from the other side and isolated that, a positive value of T would be this way. And that way, no matter which way you go, you get the same answers. How many other loads, how many internal loads did we have to deal with, remember? 4, yep. So we had to deal with the x component of the force, the y component of the force, the x component of the couple, and the z component of the couple. So I'm just going to go through all 4 of those. The other force, so this is tension, compression. If it's negative, it's compression. So tension would be positive, compression would be negative. Then the y component of the force, if you're dealing with this side, it's this way. If you're dealing with this side, it's this way. This is called capital V. I'm not sure what that stands for. And this is called the shear force. And then the 2 couple components. Nope, doesn't mean anything. Right, it doesn't really have any different, like, intuitive meaning. And then about the z-axis, there's a couple that way, or if you're on the other side this way, those are capital M. That's called the bending moment. And again, the sign doesn't really mean anything qualitative. And then the last one is the torque about the x-axis. So that's a couple this way or a couple this way, depending on which face you're on. And I'm going to represent this, since this is called the torque, I'm going to call it capital T, but I'm going to do it all fancy like. So this is the torque. Okay, so let me do that same problem over again, this time with that new sign convention. So we're not going to ever deal with ones that are going into or out of the page. And really the main reason that we're not is because we don't currently, like in this class, we're not going to have a way to calculate the stresses for things that are bending in bending around more than one axis. Okay, so we could calculate those internal loads. That wouldn't be hard to modify this to do that, but we still wouldn't be able to calculate the stresses. So, and then that brings up another point. Like, so what if this is the beam and it's fixed to the wall, and you're applying, the only force you're applying is like this to it? Well, just think of it like that, and then you're fine. You know, we're going to have to do that a lot with these kind of things, you know, but that's always implied. The coordinate system just relates to the kind of the axis that the load is happening on, not really to up or down, you know. Okay, so back to the example from last time. Oh, no, I got carried away. Here, put this aside for later. Yeah, I need a step 2. And then step 2, we are going to expand, so we're not just calculating it at a single point along the beam, but we're calculating these internal loads as functions of x as you go along the length of the beam. So calculate the internal loads for the entire length of the beam as functions of x. Okay, so now back to the example from last time. We already calculated all the external loads. And so I'm going to do a free body diagram of the left half again, or not the left half, the left side of that place where we want to find the find the internal loads. So I'm including the stuff in black and I'm skipping all the stuff, the dotted line stuff. So that means we're not considering the downward 1,000 Newton force. We're not considering the couple. We did use those to figure out the external loads on the left side, and those are a downward force of 1,000 newtons and a couple with your thumb in the direction of the negative x axis of 500 Newton meters. I'll just put the units on here so we keep the couple and the force straight. Okay, and now what we did before was we called it a force vector, and we called it a couple component in this direction and in this direction. Now I'm going to use the sign convention that I just gave you for number 1. So we have a tension T, a shear force, and now our default direction is down, V, although it still has the same information in it that the y component of a force vector would. V, yep. Then the couple, that's the component of the moment about the z-axis. We call that capital M. And then finally, the internal torque, fancy T. That's right. I mean, you can, it's just a variable, I guess, but a lot of times for an external torque, I'll use the variable TR for like reaction torque. I guess it's not like a crucial thing, but yes, you always do use it for internal when you're doing internal torques. Okay, and then Newton's second law. So we have no x forces. We have this downward 1,000 Newton force, so 0, negative 1,000. Yeah. Mm-hmm. Yes, exactly. So this is, so the infinitesimal piece is this. So the blue represents the line you're looking at. The red box is infinitesimally far to the left and to the right of the line that you care about. And so we're doing our cut from all the way at this end to the far end of that infinitesimal piece.
For 1,000 newtons, would it be outside of it? Would it be a positive 1,000?
So what we're isolating is, so the piece that we're isolating is this with our desired line there, okay? So we're not dealing with any of the internal loads on the left side of that isolated sliver. We're only dealing with the loads acting on the right side of that sliver. So we're only using the sign convention of the right side. Yeah. And then we go all the way from the far end to the point that we care about. So these are still the external loads. The only internal loads are on the right side. Okay, so let's just keep going through these forces. We have the 1,000 going down. We have the tension going to the right, so the positive x direction, so that's T0. The V is in the negative y direction, so now writing this in vector form, that's 0, negative V. That can be a little confusing. But if you always just think about the arrows here, so whenever you're looking at the free body diagram, you have an arrow that represents a unit vector, and you're multiplying it by a number represented by the variable. Okay, so what's a unit vector in the direction of this downward force? 0, negative 1, multiply that by V, and you get this vector 0, negative V. Okay. And that's all the forces. So set that equal to zeros. And you get that there's no internal tension. And the internal shear force at that point is negative 1,000 newtons. And now we'll do the moments about let's do the z-axis first. So we're using the rotational Newton's second law about the z-axis. And our about point is going to be this. It always is, all the way at the left end. It doesn't have to be, you know, from statics it could be any point, but this is just going to make the math a little simpler. Okay, so what produces moments about the z-axis with this as the about point? Not this one, that's in the negative x direction, right? That doesn't have any z component. Not this one, because it acts through the about point. Okay. What about the tension T? No, the line of action goes through that point. What about the torque T? No, that's x direction. M does, though. That's a couple about z. And what about V? It does. And so let's see. So the only ones we have are M. So adding on that couple M. And then what's the moment applied by this V? Yes, exactly right. So it's V times this length, okay? And in our case, that was 0.25. If you look back at the original problem, this was right at the midpoint. So that distance is 0.25. Let me draw that up here.
So then the moment made by the 1,000 newtons.
Yep.
So the last time the 1,000 had a distance.
The 1,000. So this is also 1,000. And that would produce a moment if that was acting on the body we isolated, but it's not. It's acting on the ghost part, you know. So that's the one that produced a moment about this end last time.
Okay, because I think for the last round that we did before we did all this, we did about the sliver. So the 1,000 on the left side it produced the moment. So then, but this time we did it about that point.
That would be a pretty crazy place to put the about point for these kind of problems. But yeah, if I did that, I don't know what I was thinking, but
it should be about the point.
We want to always do it there.
Okay.
Yeah. Okay, so we definitely have that couple M. That just gets added on. That doesn't depend on the about point. And then we have, and what's the sign of that moment that's V times 0.25? Negative, because it would cause a clockwise rotation. So that's minus 0.25 V. Yep.
What about because I know we drew it as negative,
Mm-hmm.
but because our answer came out negative, doesn't it shows the wrong sign?
No, so what this is saying is, this is just saying, what is the direction of the vector going to be, say, if this V is positive? Like, think about it that way. So say we get a value of 100 for V, okay? Then this says that that's going to be a force vector of 100 in the negative direction. And then the sign convention for the moment says that that's going to produce a clockwise rotation and negative rotation. Okay, so we got this. Then there's nothing else that produces moments about the z-axis, so that's equal to 0. And so this says that m is equal to 0.25 v, but we already know v from the step before. So that's, 0.25 times negative 1,000. And so m is equal to negative 250. And this is Newton meters. Any questions about that one? And then the last one is we have to do the x component of the moment equation. These x ones, since we're assuming that this beam has no thickness and we're going to keep doing that for these calculations, all we're going to ever be dealing with are these couples along the x direction. So all we have is a 500 Newton meter couple in the negative x direction and a positive t couple in the x direction. Okay, those are the only things that produce moments about the x-axis. So we have negative, what was it, 500? Plus fancy t is equal to 0. So fancy t, that internal torque, is equal to 500 Newton meters. And what changed this time is now, if instead of isolating this piece, we isolated the piece in the dotted blue and calculated the internal loads with all of these, using the sign convention that I gave you, so all these would be opposite, we get the same values for those internal loads that we just did. There wouldn't be the Newton's third law problem of everything being reversed. Okay. So what's the next step? So now we want to figure it out, not for just that single point, but now what we want to do basically is we want to isolate a piece like this that doesn't have a length of 0.25 meters. It has some arbitrary length x, yep. And we're going to calculate all these in terms of x. And once we have that, in this case, that'll be a function that represents the whole beam. We'll see that you have to do it as a piecewise function in most cases, but this one will work as just a single function. Okay, so now we're going to isolate a piece on the left side of the beam with length x. So I can draw it the same way that I drew this one. And we're still ignoring all this stuff on the right side. We have a downward force over here of 1,000. A couple of 500 this way. And then we have the internal loads, P, V, M, and fancy T. And this time, this length here isn't a quarter, it's X. Okay, but you can imagine, I mean, nothing conceptually is going to change about how we approach this. It's just, I mean, where was the only place in our last calculation where that length came into it? Yeah, and calculating the moment M. And so this time, when we sum up the moments about the z-axis, we're going to have this M, and we're going to have this B times X, you know. But that's what's going to give us the bending moment as a function of X. And notice that, so the idea here is, I drew it as a single piece, but the idea is that this represents everything from a tiny little piece at this end to almost the whole thing, almost all the way to the end, okay? Because it doesn't work for the whole beam, because if you go all the way to the end, you have this force here and this couple, right? But for everything from, you know, so everything that this represents includes everything all the way to the left, but it doesn't ever include everything all the way to the right. So it includes this piece, this piece, this piece, this piece, this piece, this piece. All that changes is X. And that's how we're going to get the function. Okay, this free body diagram is representative of all these infinitely many pieces of beam that start at the left and end somewhere before you get to the end. Are you with me on that kind of?
Does it matter if any of the one with the escape nuclear?
Oh, we do have that, don't we?
Is that
Yes, it does. Dang it, I forgot about that thing. So yes, okay. So thank you. Yes, that's very important. So we are also leaving this off, right? That's not acting on this thing. So what we're going to have to do is a piecewise function where for all x's between 0 and 0.5, this free body diagram represents the body. Okay. Then for all pieces from x equals 0.5 to 1, our free body diagram is going to have to include that piece. Okay. So let's see. So let me write this down. This free body diagram represents everything from, okay, so at one extreme is this, where we're leaving all this off. And you have this downward force, this couple, these internal loads. Okay, but we're leaving off this, this, and this. Are you with me on what that's supposed to look like? 2, at the other extreme, you have this downward force, this couple, these internal loads, and then we're just missing getting to the next one, and we're still ignoring these. Okay. So this represents like, this one represents x equals 0.00001, you know what I mean? And this one represents x equals 0.49999. Okay. Okay, so from this free body diagram, let's do Newton's second law. For the forces, there's the downward 1,000 Newton. And I guess I didn't explicitly say this, but like, even though obviously those, the lengths of those look very different, look at what loads are applied, and this sort of general description of what's going on applies to this and to this. The only difference is that x value. Okay, are you with me on that? All right. So the forces, we have a 0, negative 1,000. And then we have a T0. And then we have a 0, negative V. And those add up to zeros. So from those two equations, you get that T is equal to 0 and V is equal to negative 1,000. And now we'll add up the moments about the Z-axis. Our about point is where it always is, right at the end. That 1,000 doesn't produce one, the 500 doesn't. The only things that do are the M and the V. And so we have plus M minus Vx is equal to 0. We know what V is, so this tells us that M is equal to negative 1,000 x. Because M is equal to Vx and V is negative 1000. And then we'll add it up for the x component. You have a 500 Newton meter couple in the negative x, well, in the x direction, negative 500. And then you have fancy t. So negative 500 plus t is equal to 0. And so t is equal to 500. Okay, so where are these functions valid? We came up with these functions. I mean, only one of them looks like a function of x. But what we figured out is none of the other ones change as x changes. Where are these functions valid, though? For what x values? So these are all valid on the interval x between, so this, which is basically 0, just a little bit to the right of 0, and this, which is basically 0.5, just a little bit to the left of 0.5. So these functions are valid for x between 0 and 0.5, not including the endpoints. And so now based on this, so now we've done a calculation that represents all of the x values, all of the points along the beam until right before you get to that roller. T, V, and fancy T, they don't change, so we don't have to worry if the different points aren't any different. This one does change though as x changes. So based on this bending moment, where would you be most concerned about this beam breaking? Would it be close to the left end of the beam or close to the roller? Yeah, it's close to the roller because you go from an m value of 0 to an m value of absolute value of 500. Okay, so if this is going to break anywhere over the region that we've looked at so far, it's going to be as you get close to the roller. Yep. It's really the same thing, except bending is this, and torque is twisting it. Okay, so those are just the different axes. Yep.
Oh, sorry, I don't know if you mentioned it, but where does the T and the shear stress come from? Or those compared to the last one?
Oh, those are the components of the force, of the reaction force.
That's just because of the new sign convention.
Yeah, that's right. We just gave them new names and a new sign convention. Yep.
But they're replacing RA.
Exactly.
Okay.
Yep. Not RA. They're replacing probably R. What did I call it? They're replacing. Yeah, I called it R last time. It's the internal force.
And then we know that V goes down because of.
Who knows? I don't know why actually. All that matters is they had to give it a new sign convention, one that has different values, different signs depending on which way you're working. And I don't know what the reason is. There must have been some reason that it made more sense to them to choose a positive value of the shear force to be going down on that side.
But we know what direction, why is it that we chose this for our problem specifically?
This is what we're always going to use because this is what everyone uses. That's all. Always going down if you're working on the left, on a side, on a piece on the left.
Well, on the right side going.
It would go up. Yeah, but we're never going to do that. We're just going to always work from the left.
Okay.
You could though, and if you ever have time, try doing a problem the other way and see how they relate to each other. Okay, so now, well, that free body diagram, this one doesn't apply to pieces, for x values bigger than 0.5. So now we need a new free body diagram for the second half. Okay, so this time a representative free body diagram has to go past the roller. Okay, we're still skipping some of the beam. So this time the external loads we have are the 1,000 down, the 500 to the left, that's the torque, the roller at the midpoint, and that has a value of 2,000, and then the internal loads, T, V, M, and fancy T. And now we're going to call this whole distance X. Okay. And this represents everything. So this free body diagram represents everything from this where the roller's right there. We have the force, the torque, and then the internal loads. And for this one, X is equal to 0.50001, something like that. To one that covers almost the whole length, where we're only excluding just a tiny little sliver, but it's the tiny little sliver that has these external loads on it. We still have the force from the roller here. We still have the internal loads. And this one is what's X equal to in this picture? Yeah, exactly. It's just right up until you get to that end. Okay. So let's quick do this calculation. So Newton's second law, we have the downward 1,000 and the upward 2,000. So 0, negative 1,000 plus 0, positive 2,000 plus the t in the positive x direction plus the v in the negative y direction. And so here we get t is equal to 0 still. This time v is equal to positive 1,000 newtons. And now the moments about the z-axis. Our about point is still going to be all the way at the left. The 1,000 doesn't produce one. The 2,000 does. What's the moment arm of that 2,000? 0.5. Yep. Because this distance doesn't change depending on where this is. You see that? The distance between the left endpoint and that roller is fixed. Okay. So, and that would be a counterclockwise moment. So we have positive 2,000 times 0.5. And then the only other ones are the m and the minus Vx is equal to 0. And so our function for m is 1000x minus 1000. And then the last one is for the x moment. So just add up the torques. That comes out the same as it did before. There was no torque, no additional torque happening at that roller. So we just have negative 500 plus fancy t is equal to 0. So fancy t is equal to 500 Newton meters. And so the first one we did, we got these functions that were valid for x between 0 and 0.5. This time we got these functions that are valid on the interval x between, what are the values here? 0.5 and 1. And altogether, those make a piecewise function. So these give piecewise functions representing t, v, m, and fancy t along the entire beam. If you plot those as functions of x, you can, easily see where they're at maximums and minimums and stuff like that. See where you're concerned about this beam breaking, where you want to do some kind of stress analysis. Any questions about that? Okay, that's it.